Hi, I'm Xingyuan. In this video, I'm going to shortly introduce the main idea and the result in our TMLR paper, Overcoming Knowledge Barriers, Online Imitation Learning from Visual Observation with Pretrained World Models. This is a joint work with Philip, Patrick, and Max. First, let's talk about the problem we are trying to solve in this paper, the imitation learning from observations. We mainly consider a case with visual observations, and the agent is given two datasets. The embodiment datasets contain trajectories with actions, which can be any datasets recorded from the embodiment. The dataset is used to let the agent make some understanding of the embodiment. And the demonstration datasets contain demonstrations without actions. The dataset is used to define the task we are interested in. The goal of this setup is to learn a policy to replicate the behavior of the demonstrator. We show an example of the setup in the bottom. The left shows the embodiment dataset, which has a variety of behaviors, while the right shows the demonstration dataset, where the robot is running, which is the task we care about. The current state-of-the-art algorithm, BCO0 and AIM, solve the problem with 3 steps. The first step, they first train an action inference model on the embodiment dataset, and then they label the demonstration dataset with the trained inference model. And in the third step, they train a policy with behavior cloning. Both of the algorithms can generate decent results on certain tasks, but the results normally cannot match the performance of the expert. So there is something missing here. So we are trying to answer the question what actually creates the gap and how we can solve it with the new algorithms. So to understand the problem, we propose a new framework which we decompose the performance gap with 2 knowledge barriers. That is the embodiment knowledge barrier, the EKB, and the demonstration knowledge barrier, the DKB. The EKB is caused by non-sufficient knowledge of the embodiment, which leads to inference error on the actions. On the other hand, the DKB is caused by limited data support of the demonstrations, which cause the learned policy generalized poorly to the out-of-support region. And to illustrate that on the figures, you can just basically compare your algorithm with the Oracle version of the algorithms. So for example, in the left, we have these EKB and DKB show both for the AIM and BCO0. So take the AIM for example. So we have AIM in the blue line as a base algorithms, and we have the MBBC as the Oracle version. The Oracle version is basically just assume you have a perfect inference for the step 1 as we talk about. So basically you can do that by just providing the true action to the agent. Then the performance gap between them, that's the EKB. And the rest of the performance gap is the DKB. And we can already see some trend from this figure, like DKB is generally decreasing as we given more demonstration to the agent. And detailed analysis is in the paper, and in this video we will directly jump into the solution. So here we first show the framework for AIM. That's our base algorithm in this paper. We had the agent in the middle, and we use the embodiment dataset to do the model learning, and we use the demonstration dataset to do the imitation learning. And first, we want to solve the EKB. We propose to let the agent to further interact with the environment and to gather more trajectories, and we store them into an online dataset. And when you train the model, you actually can train from both the online dataset and the embodiment dataset. So because your agent is already trained to replicate the policy in the demonstration dataset, so whenever you interact with the environment with the learned policy, they are generally more closer to the demonstration dataset than the embodiment dataset. And if you're running this iteration multiple times, the behavior will be getting more closer to the demonstration dataset. And once you have the data support in your model training data, that's in your online training dataset, then you will decrease your inference error and in the end shrink the EKB to 0. And for the DKB, the root of the problem is that you don't have support for other region beyond the demonstration dataset. So we ought to propose some other learning signal for the other regions in the whole space. So the solution we propose is that we first derive some surrogate reward models. This can be derived from all the datasets we have, all these 3 datasets. And this surrogate reward model will identify what is useful, what is a defined task. And we use the surrogate reward model to label the online dataset with the surrogate reward. And then the agent, during training for the policy, they training on 2 objectives. One is a normal imitation learning objective that's coming from AIM. You only train that on the demonstration dataset. And the other one, you're training from the online dataset with model-based reinforcement learning with the surrogate reward, you're just labeling. And this imagination with the word model will enlarge the space cover of the policy training, which improve the generalization of the policy, and thus solve the DKB. And compiling the both solution upon the AIM algorithm, we propose the AIM NOB algorithm, and the NOB stands for no barriers. And here is an illustration of how this algorithm run in reality. So in the beginning, you have 2 datasets. You have the embodiment dataset, you have the demonstration dataset, and they cover separate region of the entire state space. And first start training, your agent will be allowed to gather more trajectories, which is the orange trajectories marked in this illustration. And the surrogate reward model will kick in to say, okay, some trajectory are bad, some trajectory is better, and some trajectory is good. And this reward signal will drive your policy toward the region of the demonstration, which make it more similar to the demonstration. And this trajectory is also used to train the inference model, the word model in the AIM case, which help it, because the data is more similar to the demonstrations, it will decrease the inference error of the trained model, which also decrease the EKB. So in this way, both the EKB and DKB is handled in this framework. And now let's try to see how well are the solutions. So on the left figures, we had the same figure as we showed before. We had the AIM as a base algorithm, and we had the MBBC as the oracle version, and the region between them is the EKB. And first, we have a comparison that's called AIM no EKB, marked in orange. And as this is a version that we only apply the solution for EKB, so we can separate the effect of each solution. So as we can see from the result, the orange is already matching or surpass the oracle versions. That means with the solution we propose for EKB, it's already resolved the EKB. And then if we further apply our whole algorithm, that's the AIM NOB, which we further resolve the DKB, as we can see from the result, no matter how many demonstrations you provide to the agent, it can perfectly match the expert performance. And on the right figure, we showcase that even if the left figure shows with even 1 trajectories, you can match the expert performance in the final performance. But when you have more demonstrations, it's generally help for your learning speed, sample efficiency. So that's it says, if you have more demonstrations, you can learn the same task faster than before with less environment interactions, which is quite useful when you have limited capacity to do the online interactions. And last but not least, we compare the AIM NOB algorithms on common benchmarks with other state-of-the-art algorithm on this setting. So we compare AIM NOB on 9 DMC tasks and 6 meta-word tasks with other algorithms. And here is the aggregate version of all the performance. As we can see from these figures, AIM NOB presents a superior performance compared with all the other baseline algorithm with a large margin, which indicate the great potential of the AIM NOB algorithms. And details and more results are in the paper. And if you have many questions about this paper, please feel free to contact me. And thank you for your attention.